In PID control, the P stands for proportional, the I for integral, and the D stands for derivative. These three terms refer to what we do to the error in order to calculate the voltage. Remember that in feedback control, the controller is an equation that converts error into voltage. If we write the equation for the controller in such a way that the voltage is proportional to the error, then we will be using proportional control. If we write the equation so that the voltage is based on the integral of the error, then we'll be using integral control. And if we write the controller equation so that the voltage is based on the derivative of the error, then we'll be using derivative control. We can also use different combinations of these three in order to get PI control, PD control, or complete PID control. I'm going to start with just proportional control, and we'll be looking at how we do proportional control and what the effect is. And after that, we'll move on to integral and derivative control and complete PID control. Remember that in on-off control, we set the voltage to the motor to be constant. The constant voltage would either be 0, or it would be a set positive number or a set negative number, so that the motor would move at a constant velocity. In contrast, in proportional control, we're going to vary the voltage and in that way vary the velocity of the motor based upon the error. We want the motor to move faster when the error is large, that is, when the motor is far away from its target position. And we want the motor to move slower when the error is smaller, that is, when the motor is getting close to its target position. We can achieve this by setting our voltage to be equal to some constant, which we will set, times the error. And remember here that the error is equal to the target position minus the current position. By doing this, we will have a voltage of 0 volts when the target position and the current position match. That situation is the same as what we have in on-off control. We want the motor voltage to be 0 when the motor is in the correct position. When the target position is greater than the current position, the error will be positive, which means that the voltage will be positive. That will make the motor move in a forward direction towards the target position. When the current position is greater than the target position, the error will be negative. That will result in a negative voltage. That will cause the motor to turn in the reverse direction, moving the motor closer to the target position. When we use proportional control, we have to set the value of this Kp constant. We can figure out a good value to use for Kp by testing the system and looking at the motor response curve for different values of Kp. Let me show you how that works. Let's suppose that you've set the value of Kp in your control equation and you've tested the system to see what the response looks like. And let's suppose that this is the response that you see. Increasing Kp will have the following effect. An increased value of Kp will make the system faster. In other words, the rise time will be reduced. Also, the overshoot will become greater, and the steady state error will become less. In other words, the effect of increasing Kp is to reduce the rise time, to increase the overshoot, and to decrease the steady state error. Now, you can decide whether this value of Kp is appropriate for your system or not based upon what your requirements are for the speed of the system, for the overshoot, and for the steady state error. For example, in a robotic manipulator, you might have a limited amount of acceptable steady state error. If the steady state error is too large, the location of the end effector will have too much error in its position, so you might not be able to pick up the object you're trying to pick up or position the end effector to perform a painting operation or whatever it is you're trying to do. Increased steady state error will cause error in the position of the end effector, and so you have some limit in the amount of acceptable steady state error for each joint. You might also have a limit on the amount of acceptable overshoot. Overshoot will cause the position of the robot end effector to vibrate. And these vibrations could cause the end effector to collide with something you don't want it to hit, or to have undesirable move dynamics. You also might have a requirement in how fast you need the joints to respond. If you're trying to do a fast pick and place operation or something like that, you don't want the movement to be too slow. So in tuning your controller, that's what we call choosing the value of Kp, you would adjust the value of Kp until the robot manipulator and the end effector ultimately shows the kind of performance that is acceptable for the application. Now, it may be that changing Kp is not sufficient to achieve the kind of response that you are aiming for. In other words, it may be that you cannot get a sufficient rise time, overshoot, and steady state error within your limitations by setting any value of Kp. And in that case, you would want to introduce either derivative or integral control as well. Let's talk about those components next.